The last talk that we got of the summit is from UFC Calgary, Dr. Roman Shor.
All right. So, back. All right, so thank you, and then thank you, Energy Simulation, for setting all this up, and the Energy team for all the work getting this done, also dealing with us sending you slides at the last minute. We never do that, right? And also thank you to the TU Delft team for putting the Summit School together. It looks awesome. I sadly can't stay, but my students I know will love this. So I have the distinct pleasure of anchoring this. So I'm between you and the beach for the people here. I'm between you and coffee if you're in North America, and I guess you and adult beverage if you're somewhere further in this time zone or further east, right? So, Roman Shor, I'm at the University of Calgary, where I lead the geothermal research group, both as the Energy Simulation Chair in Geothermal Systems, but also as the Director of the Energy Simulation Center for Geosystems Research. So what I want to spend some time talking about today is advancing solutions for geothermal energy. Four of my students are here, so if the Calgary folks want to raise their hands, they're all hiding in that back corner. We have Nick talking a little bit about shallow geoexchange, so looking at building systems. Pratika's looking a little bit at using drilling data to look at well logs. Gordon is looking at coaxial heat exchangers for closed loop. And then Philip is looking at building systems, so that direct use there. So during that poster session, please go quiz them, give them some constructive feedback. We're open to ideas, and they're open to spilling some of the details that they've been working on for the past little while. But to begin, what I want to start with a little bit is there's been a lot of talk about AI and machine learning. So at one point, I asked Adobe Firefly, what does a geothermal superhero look like? And this is what I got. So a volcano with a geyser that looks a little bit like a pile of ice. Then four folks in front of it, one of whom has a hot water bottle on their back. So I was hoping for like more Vikings type, let's say, returns from, like, let's say, Iceland. But again, when we start thinking about AI, how do we use these tools, and how do we also, say, use these tools to help interact with the public? Because for geothermal in particular, you ask about geothermal, most people will think volcanoes, geysers, and Iceland, or volcanoes, geysers, and if it's safe, we're here in Europe, maybe all the power generation that we have in South Central Africa, maybe New Zealand, Australia, etc. So it's that public perception that we also have to change about this is that viable energy source. But what I want to do is I want to give you a brief update of what's happening in Calgary. So what the folks in the Geothermal Center are doing, some of the new finds that come out. Then I want to talk about drilling, because that's what I was asked to do and promised to talk about. But then, of course, my paper with Ever has been delayed. So I can't talk about any of the results from Everdeep. I have to base everything on Utah Forge as usual, and then just hint that these are some of the things that we're looking at Everdeep. And then finally, some of the challenges and opportunities coming forward. So first off, what is our goal in Calgary? We want geothermal anywhere. So wherever you are on the planet, we want there to be an option for some form of a geothermal subsurface energy type system. And we want to do this through that multidisciplinary approach where we look at geology, geoscience, connected that with the subsurface wells, with the surface equipment, with that direct use, but also with this is enabling that discussion and, let's say, that connection with the community, with policy, with law, in order to actually make these systems happen. Because frequently, especially us as engineers, we design something and we think it's the best thing on the planet, which should be built, and then the public comes in and says, no, we don't want this. So how do we start working around this? Just quickly on the focus areas, we try to span this gamut. So looking at everything from understanding this geology and geophysics, this heat flow, particularly focused on Western Canada, looking at the heat flow modeling itself from the pore scale to the well scale, or sorry, to the borehole scale to that well scale, looking at the well designs, how do you flow this heat through it. I've kept this potato masher concept in here now for quite a while. So can we actually drill a well like this? So for those of you who have ever made mashed potatoes, you may have used one of these. Is a well like this possible? What can we do to increase this subsurface area for this heat transfer? Short answer is no, we can't drill that, but there's probably something more something similar that we could. And then finally, that surface heat recovery and use. Then with all of this, looking at how do we enable utility scale and microgrid scale adoption? So working with developers to develop, let's say, a 5,000 home community that's all going to be on a single system when everyone who's buying is used to having an individual furnace at home. How do we enable that? How do we enable that discussion? How do we, let's say, work with local communities, let's say both in southern Alberta and the far north, and then also educating communities. So if a city doesn't understand what geothermal is, they will probably be a barrier to entry of, let's say, these systems because they don't understand how to actually install these systems in their roadways. And then finally, working with those remote communities. So some recent projects, let's quickly highlight them. So a student presented this at Geothermal Rising 3 weeks ago. Can you use a Everloop, so closed loop geothermal, to produce green hydrogen? So power comes out of that geothermal loop. It provides you that base load, water comes in, you have an electrolyzer, and you have hydrogen that comes out. Sounds like a fairly expensive proposition, but what if you are trying to provide a hydrogen refueling station in a remote area? So between two cities on a highway, you need to refuel. So what are the options? You have a tanker that transports it in, or you make it on site. So this is an interesting opportunity, let's say, to do it on site. And what was found, again, the drilling costs are frequently called out, but using Ever's estimates for drilling costs, producing that power on site in, let's say, California or potentially parts of Alberta could be on, let's say, cost parity with producing it from another type of renewable. Reason for this is your other renewables are intermittent, so you only are able to produce for a third of the time, while that geothermal allows you that constant production. Another thing we looked at is, let's say a community wants to enable geo-exchange locally. What type of, let's say, feasibility mapping do we want to do? So what Maren was talking about earlier on that, let's say, that country scale, can we now start scaling down to the city scale and identifying what types of systems are best suited for specific areas? Maybe an open loop geo-exchange system, which is aquifer flow, is better in one area because you have aquifer flow or, let's say, saturation, while in another area, a closed loop system, because you have in bedrock, might be better. So how do you now identify which of these should be that first thing that you look at? So we're working with communities near Calgary and the mountains about trying to enable this. One other thing that we looked at as well is how do we enable heating and cooling that's more energy efficient, lower carbon intensity, and also, I'd say, lower cost in southern Alberta. So for those of you who aren't aware, southern Alberta has a temperature range from about plus 35 in the summer to about minus 35 in the winter, so a 70-degree temperature swing. And a lot of our homes need air conditioning in the summer because they're very well insulated, and they need a lot of heat in the winter. So what are those alternatives to actually heat and cool these homes? So if you start thinking about, let's say, replacing things, what are the economics, what are those carbon intensities, et cetera? So what we're finding is if you want to install air conditioning, get a heat pump, get a cold climate heat pump, and all of a sudden you have a very energy efficient system that reduces your carbon emissions by half to, let's say, 3/4. Geo-exchange, drilling is still a bit of a challenge. I got, again, my Ever post got a lot of call-outs on why is the Everloop so cheap. I instead got a lot of call-outs on why is my borehole array for ground source so expensive. So at one point, I overestimate, get called out on it. On the other side, I underestimate, get called out on it. It's fun. All right, so these are some of the things we're looking at. But talking a little bit more now, and then one more, we are also looking at what is a possible system for the University of Calgary to produce heat for the entire campus. So Delft, you're looking at open loop, you're flowing through that reservoir, and you're doing high temperature storage. Is it possible to do closed loop at about that same depth? Because we have a nasty problem called H2S in the subsurface. Can we use that same depth, that middle deep type system? And then can we store heat directly in that middle deep? So in the winter, we inject, let's say, at 15, produce at 30 or 25. And then in the summer, we inject at 70 and then produce at 60. So we can balance that system out that way, and we can have seasonal storage. So this is a system that we're still working through that engineering on. It might be in that demonstration phase sometime in the near future. So this is all coming. There's a lot more stuff coming from us. But again, looking at this type of a closed loop design, This is a lot of wells. So I think this is going to be about probably 70 to 80 kilometers a well. Me as a driller thinks this is heaven because there will be drilling going on for a very long period of time. So how can we now use this and build upon this to optimize it? So just as a brief introduction, how do we drill? We start with some surface equipment whose entire role is to rotate, lift, and flow. We transmit all of this power along this really fancy steel pipe, which is just literally a piece of pipe. And then we end up at this little thing at the bottom called a drill bit, which we beat up, but we want this to last as long as possible. Now, the problem with this is we know very little about what's actually happening in the subsurface. We have all the information available at surface, so this is our surface data recording. It's frequently only 1 second though, so there's a lot of it, but you may not be capturing everything that's happening. And then downhole, you may have sensors down there, but there's very little available real time. So if you start thinking about control, how do you enable closed loop control when you can't measure something in real time, or if you do, there's very little data that's coming from it. So ways that we can think about this is looking at different metrics for performance drilling and different models to connect that surface and subsurface. So just, if you think about performance and we're trying to extend, or say, speed up how fast we get from the top to the bottom of our well, one way we do this is through something called energy. So we look at the energy we put into the rock breaking, and then we compare that with the energy we think the rock should take in order to break. So we compare this input energy with the compressive strength of the rock. So the mechanical specific energy versus the CCUS. There's this very simple equation that's been around for a very, very long time. And then we can see this energy efficiency, or this bit efficiency now, as this ratio between the rock strength and what we assume as our input energy. But the problem with this, it doesn't account for well bores that are non-vertical, torque and drag. There's energy loss along that drill string. There's hydraulics, there's vibration, there is thermal effects. There's all sorts of interesting things that are coming in as part of this. So my proxy, since I'm not allowed to talk about a certain project in a certain southern state with a certain company, I will be talking about another project in a state just north of it that is all public. So this is Utah Forge. And these references are coming from Sam Nornert and Fred DePriest at Texas A&M that they published over the last 2 years. So what they did is they went through and they worked with the drillers at Forge in order to optimize drilling. So in 2021, if you ask somebody, what's the fastest you can drill through granite? The answer you would get is 1 to 3 meters per hour. So you would have wells that take months to maybe even a year in order to reach 3 kilometers. So they started with that. So that's, let's say, this first well that they drilled, and they started thinking about what could be done to improve that drilling performance. So one of the first steps was push harder. Improve that weight and bit, improve that energy transfer to that drill bit, and start monitoring this overall energy. If you are seeing energy like dysfunctions or energy dissipation, do something about it. The next thing they did was they looked at the hydraulics, reduced the mud weight, so used water instead. That gave them that next step. And then finally they changed to PDC drill bits and started, let's say, looking at PDC drill bit design. And they went from 1 to 3 meters per hour to 30 to 40 meters per hour. So a 10-fold increase simply by changing that technology. And with this, they were able to let's say, achieve bit runs that were maybe, let's say, a third to a half a kilometer long. The certain company that I worked with was able to replicate this with certain other challenges down in New Mexico. So where this becomes interesting is looking at this performance of the drill bit over time. So every single bit run, so what we have here is we have 4 different bit runs. So if I can get this to move. So we have 1 bit run here, a 2nd bit run, a 3rd bit run, and a 4th bit run. This is approximately 3,000 feet or 4,000 feet of drilling. So this is about 1.5 kilometers. And then each time you're drilling, so this rate, the green curve is your rate of penetration, so your speed of drilling. And then your, let's say, red curves over here are your torque. So this is that effort you're putting into drilling. Every single time that they were drilling, they started off drilling at a very high speed, and then they rapidly dropped off to a low speed that was consistent for a while, and then they achieved something called bit death. So the bit died every single time, was pulled out in complete pieces. So this is called DBR, so drill bit beyond repair. But again, you have this very, very consistent performance. Why is this? And then what can we do in order to make this initial portion let's say last longer? So my little pointer works. And also, how do we keep this, let's say, this flat portion higher and longer as well? Because every time you pull out a hole, pull that drill bit out and put it back in, that's 1 or 2 days. So if you can avoid these, this is going to save you a huge amount of time. So what you can do for this is there's various ways of starting to think about it. One of them is the drill bit is falling apart, so the bit is wearing. So what we have now is different ways of operating. Could we, let's say, limit our drilling speed, and then at a certain point when we are having to push too hard to maintain this speed, then start to drop off, let's say, our speed limit? Or should we drill at full speed and then just simply lose speed as we're going? So if we're thinking on the highway, should we drive as fast as possible for as long as possible as parts are falling off my car, and then as the car continues to fall apart, you slow down? Or should you drive at a certain maximum speed on that highway until enough has fallen off that you start to have to slow down? So when we think about it, what's really happening on that small scale is your little diamond cutter is sliding across this material and it's removing a layer of rock. It has a certain sharpness and it wants to remove that rock layer. That sharpness reduces rapidly in diamond. So diamond is strong, granite is also strong. Hot granite is, let's say, a little bit more ductile, but hot diamond is very brittle. So how do we manage these different things now in order to say we want this cutter to remain as sharp as possible and remove as much rock as possible as well, while maintaining, let's say, the sharpness as you're going on? So this is a typical series of bit wear, where you start with a very sharp rock or a sharp bit. You start wearing it flat, and then at a certain point, you've worn too much off, so you're starting to lose significant pieces off of this drill bit. And then with this as well, is as you're drilling down, your car driving down the highway falling apart, it's cataclysmic. You're driving along, you lost your hood, oops. You lose your hood, you lose a door, you lose the windshield, whatever, you're still fine, then all of a sudden the wheels fall off. And that wheels falling off portion happens within the course of about 5 meters or less. So how do you monitor, and then how do you also predict my wheels are about to fall off? Because you don't want to take that exit with your wheels still attached, but you also don't want to push it too far to the point where the wheels have now fallen off. So you want to find that balance between the two of them. So, and then finally, if we're starting to think about a bit hydraulics a little bit, what is that effect of the cuttings being lifted off, and how does your drilling fluid affect that? What new technologies could we use to combine all of these in order to really improve this rock cutting effect? So, and finally, as you're drilling as well, thinking back to that analogy of the car, as you drive along, bits and pieces are falling off. Are you tracking straight, or is your car starting to wobble back and forth? Like you're on the highway and you see that car driving sideways because its alignment's off. So are we driving sideways? Are we driving straight? What's happening? And with this, the borehole patterning is a very interesting one, where you can start seeing what is the effect of your operation on the borehole, and what's the effect of the geomechanics on the borehole as well. Because you are cooling this formation as you're drilling. What happens to that hoop stress, and how does that affect borehole breakout? And how does a 11-inch bit drill a 14-inch hole in granite? Those are some of the things that we've seen. All right, so that's the instability portion of it, understanding that hoop stress. So this is where that geomechanics, rock strength, geology portion really tie in with the drilling to understand that interaction between the two. All right, so what we're doing to understand this is we have been looking at rotary percussive drilling, where we are looking at the effect of percussive rock failure, so compressive rock failure from impacts of a diamond cutter, and looking at how that affects the overall bulk matrix. So what we have here is we have a picture of, let's say, a core. So this right here is that impact site where we've been hammering with a piece of diamond. The labs that's below me in my building loves me, because every once in a while they hear a loud clunk as a hammer is being dropped on a rock. This little hammer impact site looks a little bit like this if you send it through a CT scanner. So you have that nice round crater shape, and it has, let's say, some form of a 3D reconstruction, which may be symmetric, maybe not, based on an environment. Now, if we go in and take a look at, let's say, this wall, so let's say approximately here, and look at it in the SEM, what we start seeing is we start seeing some patterns within the overall micro cracking along the actual structure. So there's one here, there's a second one here. So how does this impact affect the rock that remains? So not the chip or the cuttings that are removed, but the remaining rock. And then how do we optimize where we hit the next time? So for rotary percussive, there's an idea of how do we now time those percussive blows as we rotate in order to maximize that rock failure. Similarly, if we're looking a little bit at rotary drilling, we have, let's say, our piece of rock that we're rotating. We are cutting away on that central surface. This part, let's say we are grinding. The outer edge, it's unconfined, so it's failing, let's say, just due to no confining stress. The interesting thing is the cuttings that we got off of this unconfined rock, so this outer edge, were shockingly similar to the cuttings we got out of the hole. Why is that? What interesting things are happening down hole to create these types of cuttings that look very similar to our unconfined cuttings at surface conditions? And then also what we found is our poor little cutter got destroyed within about a millimeter or about a centimeter of drilling. And part of that reason was that this is a thermal camera. Where's my, okay, so the last image is a thermal camera looking at that heat that's being generated by this cutter. So you can see that right at where that cutter is, you have a spike in heat and then a slow dissipation of that heat as it continues to rotate. So there is a instantaneous heating of the rock right at that cutter, which then also affects the diamond surface, also affects the rock. So you have this interaction now between all of these. So how does all this fit together? So we're putting, so a lot of theoretical work, a lot of experimental work is currently going on to understand this. We're also putting together a tool to operationalize this. So for any drillers in the room, this type of screen looks somewhat familiar as it's your typical well viewer, Payson, data viewer type system where you have time-based data on your various drilling parameters. Can we augment this with the ability to label data? So once we start thinking about machine learning, we have this labeled data set. And then can we start applying physics-based or data-driven models to this to try to, say, forecast it? So this is the, let's say, the MVP product for this. And now this is the current view of what the system looks like, where we now are able to label data, auto-characterize some of this data, and apply basic workflows to it. So this is now being applied in the field over in Garrett Strait. So this is Everest project in Germany, where they're drilling the 2 wells in parallel, where they'll be drilling for the next 2 years. So this software will be used there. So with this, I think I'm more or less at time. So I just want to thank all of our sponsors. One person that I met a couple weeks ago fondly called this logo soup. So this is my version of my logo soup. It has a little bit of a mountain flavor to it. But thank you to our government partners. A huge thank you to Energy Simulation and also to Everett Technologies as our 2 leading sponsors. And then this is a picture of the summer research team that we had this past summer within the group. So I think with that, some references and questions.
Questions? If not, they can always follow up with you. Yeah, thank you, Roman, once again.